Chapter 12.1 Comparing two or more population proportion. To introduce the technique to compare two or more population proportion, we'll rely on the following example. The writer of a recent article in Bloomberg Business Week 1 states that on Wall Street Monday is the best day of the week. So what do you think? Is it true? The information was based on the number of days that S&P 500 index increased and decreased by weekdays over the course of a 6-month period. Table 12.1 shows the number of times the market was up and the number of times the market was down for each day of the week, along with the total number of observations for each. The last column in the table shows the proportion or percentage of days the index increased on each weekday. The statement in the article is based on the fact that on 80% of Mondays in this sample, there was an increase in the S&P 500 index. This was a higher percentage of up days than any other day of the week experienced. The term for in chapter 12.1 refers to the observed frequencies. We are interested in determining if the proportion of up days truly different across days of the week for the S&P index, which would provide support for the claim made by the Business Week article. In other words, do we have enough evidence from this sample to support the writer's statement that Mondays have more up days than the rest of the weeks as a general rule? Does the information present a real pattern we could rely on as investors to make decisions? Step 1. Identify the null and alternative hypothesis. The hypothesis statement for this test is very similar to one-way ANOVA from Chapter 11 for the S&P 500 example. It is as follows. Null hypothesis, P1 equal to P2 equal to P3 equal to P4 and equal to P5. Alternative hypothesis, not all P's are equal, where Pi is the proportion of up days for the ith day of the week. As with our previous hypothesis test, we need to identify our significant level, which is the probability of committing a type 1 error. For this example, we will set the significant level to alpha equal to 0.05. Had we chosen a lower value for example, 0.01, we would reduce our chances of incorrectly rejecting the null hypothesis. In other words, we would be less likely to conclude there is a difference in the proportion of up days among the weekdays, when in reality there is no difference in the population proportion for the S&P index. Step 2. Calculate the expected frequencies. In this step, we calculate the expected frequencies, which are the frequencies that are most likely to occur if the null hypothesis is true. We are assuming that the proportions are equal for each weekdays because, like rolling a die, that is when we would expect to see if the number of up days were purely random. Consequently, we need to calculate the overall proportion of up days. From table 12.1, we recorded a total of 78 up days from a total of 125 days. This results in the following overall proportion. P cap is equal to 78 divided by 125 equal to 0.624. In other words, 60.4% of the days during the period were up days. This proportion represents our estimate for each value of P1 through P5 under the null hypothesis. We would expect this proportion to hold true for each weekday. We use this proportion to calculate the expected frequency of updates or FE, for example, for each weekdays by multiplying NP by the value in the total day, column in table 12.1. Table 12.2 shows this calculation. We also need to calculate the expected frequency of the occurrence of downs days. We can do this by subtracting the expected frequency of up days from the total days shown in table 12.3. The chi-square test requires that each expected frequency be equal to or greater than 5. This requirement ensures that the chi-square test statistic shown in step 3 follows the chi-square distribution to be introduced in step 4. Looking at table 12.2 and 12.3, it appears that the lowest frequency is 8.65. Consequently, this requirement is met. Later in the chapter, we will examine how to handle the situation when this requirement is not met. Step 3. Calculate the chi-square test statistic, or X-square. The test statistic for the chi-square test for 2 or more proportion is shown in equation 12.1. The chi-square test requires that each expected frequency be equal to or greater than 5, where X2, X square is the chi-square test statistic, FO is the observed frequencies, FE is the expected frequencies. If the null hypothesis is true, the logic of the chi-square test statistic is as follows. If the observed frequencies are close to the expected frequencies, the term FO minus FE squared in equation 12.1 will be small. This will result in a smaller chi-square test statistic, which increases the likelihood that there is support for the null hypothesis. If the observed frequencies are far apart from the expected frequencies, the term FO minus FE squared in equation 12.1 will be large. This will result in a large chi-square test statistic, which increases the likelihood of our rejecting the null hypothesis. Table 12.4 assists us with this calculation. Column 1 and 2 are the observed and expected frequencies from table 12.1, 12.2, and 12.3. The remaining columns were determined as follows. Column 3, column 1 minus column 2, column 4, column 3 square, column 5 is column 4 divided by column 2. If the null hypothesis is true, or NP is close to the same value for each day of the week, we would expect the chi-square test statistic to be close to 0. Think about it. Under this condition, the values for FO and FE would be very close, making the difference between these values almost 0. On the other hand, if our test statistic is very large, we have evidence that the null hypothesis is not true. Step 4. Determine the chi-square critical value, X square alpha. The test statistic shown in equation 12.1 follows a new distribution, the chi-square distribution shown in figure 12.2. As you can see, this distribution is right-skewed, and the rejection region lies in the right tail. The chi-square test for proportion is always one-tail or apple hypothesis test as shown in figure 12.2. This is because the chi-square statistic in equation 12.1 will increase or move toward the right tail under either of the following scenarios. 1. When observed frequencies are less than expected frequencies. 2. When observed frequencies are more than expected frequencies. This is a result of the square difference of observed and expected frequency, or FO minus FE squared, in the numerator of equation 12.1. The chi-square distribution has degree of freedom, or dF, equal to k minus 1, where k equals the number of categories. In the S&P 500 example, the categories are the weekdays, so k equal to 5. The critical value for the chi-square distribution, x squared alpha, can be found in the table 8 in Appendix A. An excerpt from this table is shown in table 12.5. For our S&P 500 example, we have k minus 1 equal to 5 minus 1 equal to 4 degrees of freedom. Using the alpha equal to 0.05, table 12.1 indicate that our critical is x squared alpha equal to x squared 0.05 equal to 9.488, highlighted in red. Another way to determine the critical chi-square score is with Excel chi-square.inv.rt function, which has the following characteristic. chi-sq.inv.rt with two parentheses alpha and degree of freedom, where alpha is the significant level and degree of freedom is k minus 1. In this case, k is the number of categories. For our S&P 500 example, we have chi-sq.inv.rt 0.05, 42 equal to 9.488, which match the value from table 12.5. Step 5. Compare the test statistic x squared with the critical value x squared alpha. This comparison is used to decide whether to reject or fail to reject the null hypothesis. To do so, we use the decision rule shown in table 12.6. Because x squared equal to 5.09, which is less than x squared alpha equal to 9.488, we fail to reject the null hypothesis according to table 12.6. We can see this graphically in figure 12.3. The test statistic, or x squared, is clearly in the white do not reject region. Step 6. State your conclusion. Recall that our hypothesis statement was as follows. Null hypothesis, P1 equal to P2 equal to P3 equal to P4 equal to P5. Alternative hypothesis, not all P's are equal. By failing to reject the null hypothesis, we do not have enough evidence to conclude the population proportions are different. Notice that this is not consistent with the claim by the Business Week article that Mondays is the best day of the week for the S&P 500 index. I hope that you agree with me that this statement has little statistical merit, but sound convincing coming from a well-known publication such as Business Week. As tempting as it is to believe Business Week and alter our investment strategy, we just don't have enough evidence to confirm the publication claim because we fail to reject the null hypothesis. This Business Week article is guilty of using a sample to make an erroneous conclusion about a population. This is a great example of the benefit of statistics in the business world. Thank you.